You may already know how to take the derivative of simple functions, such as polynomials, trigonometry ratios, exponents, and logarithms. This is easy. Simply use the power rule, or remember the identities. But what happens when you get something complicated like this? What is this? Where do we even begin? Which parts do we differentiate? In order to find the derivative of complicated expressions, we'll need to learn new differentiation rules. These are applied to situations where functions are multiplied, divided, or even placed in one another. Let's take a look at the product rule. Here's an example. We need to find the derivative of y equals to the product of 3x plus 4 and 2x minus 3. I know what you're thinking, can't we just expand and differentiate using the power rule? Well, the thing is, the product of two functions isn't always something simple and nice. What would you do if there's a tricky exponent or a trigonometric function? Well, what do we do now? The product rule simply states that the derivative of a product of two functions is the first function times the derivative of the second function plus the second function times the derivative of the first function. The derivative is equal to 3x plus 4 multiplied by 2 plus 2x minus 3 multiplied by 3, which is 6x plus 8 plus 6x minus 9. After combining like terms, we can get dy dx is equal to 12x minus 1. This can apply to all of the other complicated examples too. Yes, that's the neat thing about these rules. But how do we know that this is true? We can use the first principles of calculus to prove it. This proof requires some tricky manipulation, but it's very satisfying. The trick is to sneakily add and subtract these additional expressions, which factor out nicely with f of x plus h and g of x. Then we can rearrange some terms to get the product rule. Now we can look at the quotient rule, which we can use to find the derivative of a function divided by another function. Hey! The numerator here looks similar to the product rule. Yes, but note that it's a subtraction instead of an addition. And the order matters too, the derivative of the numerator function times the denominator function minus the opposite. And all of this is divided by the denominator function squared. We can try a harder example this time. Y equals to 3x squared over sine of x, 6x times sine of x minus cosine of x times 3x squared, and divide everything by sine squared of x. Here's the proof using first principles. Once again, the tricky part is adding this addition and subtraction of f of x times g of x and factorizing everything out. It's important to recognize that these factorizations here are just the derivatives of f of x and g of x. Finally, let's learn the chain rule. We use this to find the derivative of a function of a function. The important thing when doing chain rule calculations is to know which are the outer and inner functions. Think of it like peeling layers on an onion. We want to differentiate the outer functions first, then the inner functions, and multiply the results together. Let's try y equals to the natural logarithm of 1 over e to the power of x. This is a hard one. To differentiate, we can use our onion analogy. First, identify the outer function as simply being the natural log of whatever's inside. So differentiating it would get us 1 over e to the x, or just e to the x. Moving on to the inner function of 1 over e to the x, which we can also write as e to the negative x. Here, we can apply the chain rule again, recognizing the second outer function as e to the power of the inner function, which is just e to the negative x again. The derivative of the negative x is negative 1. Now let's multiply e to the x by e to the negative x by negative 1. This simplifies very nicely to negative 1. Wait, it's that easy? Well, it can be, if you know what you're doing. As for proving the chain rule, this is left as an exercise for the viewer. Just kidding, this is a classic math joke. The rule is quite difficult to prove rigorously, but we'll use first principles to show how it works. As you can see, it includes a sneaky multiplication right here. You can pause the video and look through it.